Okay, so there's one slide we have left to finish from 6.2, and then we'll look at 6.3. So let's take a look at sine and cosine. And I'm actually going to show you a picture of them because this is going to lead into what we're going to do in the next section. Let me show you the graph of sine. If you look at it, it looks like a wave, and it will continue that pattern forever. Does it look like there's any holes, breaks, or vertical asymptotes in that graph? No, it's a continuous function. And if you zoom out, you're just going to see more of the same pattern. So what do you think the domain is for sine? If there's no holes, there's no breaks, there's no asymptotes. Yeah? Yeah, it is. The domain for sine is all real numbers. It's negative infinity to infinity. And if you say, well, you also mentioned cosine. Okay, well, cosine looks very similar. It's basically a horizontal shift. That's all it is. Same domain. Now, range. Does it look like the graph goes up and down forever? No, it definitely has limits to it. Sine and cosine have the same limits. Anyone think they see the highest and the lowest that sine goes? Tyler?
1, negative 1?
Yep, it is negative 1 and 1. Now, we're going to talk in the next section about maybe shifting or stretching. And if you shift it or stretch it, yeah, we can change the negative 1 to 1. But if we don't do any kind of transformation to sine or cosine, that is the standard range. Now, if we do transformations, could we ever change the domain? No. The domain is all real numbers. If you shift it right 5 units, it's still all real numbers. So we can't ever affect the domain in sine and cosine. But the range, we could. All right. Now, the other thing I want to take a look at is this. What did we say in degrees? You can add or subtract to an angle if it's too big or if it's too small. What's the number we can add and subtract? And it won't mess up the answer when we do trig, but it makes it easier to work with. Jake?
360.
360. So let's take an angle. Ethan, can you give me an angle?
1 degree.
1 degree? 1?
Yeah.
All right. So let's take the sine of 1 degree. We get 0.017. Let's take the sine of 1, and let's add 360 to it. Remember, we said adding and subtracting 360, it doesn't make a difference. And it doesn't. I still get the same answer. Let's take the sine of 1. Let's add 360 again. So I'm adding double 360. I'm adding 720. Same thing. Let's take the sine of 1, and let's minus 360. What do you think I'm going to get here? Same thing. I can add or subtract any multiple of 360 to a number, and it won't affect the sine or the cosine. I would still get the same answer. I'll pick the angle this time. 2. Okay, so we take the cosine of 2, you get 0.9939. Cosine of 2 plus 360, same thing. What about if you added 360 twice? Same thing. What if you added 360 12 times? Same thing. Adding and subtracting 360 doesn't affect the answer. What is 360 the same as in radians? Yep.
2 pi.
2 pi. So if you're dealing in degrees, you can add and subtract 360, and it will not affect the answer to a sine or a cosine problem. If you're dealing in radians, you can add or subtract 2 pi, and it won't affect the answer to a sine or a cosine problem. And that is what this is saying right here. You can take any number you want, including 1. or 2, or 3, or 4. Any number you want. And you can add 2 pi n. N is an integer. So you can add 2 pi times 1, or you could add 360 times 1. You could add 360 times 2. You could add 360 times 7. Adding and subtracting multiples of 360, or multiples of 2 pi in radians, won't affect the answer. You'll get the same thing as if you didn't add the 360 or the 2 pi at all. And that's called the periodic property for sine and cosine. And that's actually a good place to now jump into section 6.3, talking about periodic graphs. And that's what we're going to look at in that section. We're going to look at the graphs of sine and cosine. Okay. Any questions on those two properties? All right. So for tonight, and I'll put these on the board at the end of the video, the first part of the homework will be those 4 questions. Okay, now let's take a look at 6.3. Right, so we just finished 6.2, and we talked about the periodic property for sine and cosine. It kind of shows you what you can do numerically, basically what you can add or subtract, and it won't affect the answer. Well, now we're going to think about that a little bit more visually. What do sine and cosine look like when you draw them? So these two functions are what we call periodic functions. Okay, so this is kind of tying in with the last thing we just did. And the reason they're called periodic functions is because after you've drawn enough of the graph, you start to notice it's repeating itself. You're like, wait a minute, I already drew this before. It's the same as what I just drew a minute ago. So what happens is the y values start repeating. The y values are going to be trapped. We talked about this in the range. They're going to be trapped between 2 numbers. And they're basically just going to keep oscillating up and down over and over forever between 2 numbers. So sine and cosine are what we call periodic functions because all the different y values that you are capable of getting from these functions will begin to repeat themselves in the same pattern after you've traveled a certain amount on the x-axis. So what I'm going to do now is I'm going to put the graph back up of sine and kind of explain what this means a little bit more visually. Now whether I put up the graph of sine or the graph of cosine, they're basically the same graph. I tried to show you earlier. One of them is really just a horizontal shift of the other. So let's take a look at just the graph of sine. So let me do, I'll explain how you need to adjust your window when we start to get into this more, but you can just watch for now. So what we're looking at there is what we call several cycles of sine, or several periods of sine. One full period would basically be defined to be between here and here. What I just traced in green, that's one full cycle of sine. And you can see the y values. 0. And then the next one where we hit the high value is 1. Then we come back down to 0. Then the low value we hit is -1. And then we end up back at 0. 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. That pattern is going to keep repeating. So once you've drawn this much of the graph between those two red lines, you've seen everything that's going to happen. To get the next section, all you have to do is click on that, copy and paste it, put it right there, and there's the next section of your graph. So any question on that idea of the graph repeating itself after you go beyond what's between those two red lines? You have to draw what's in those two red lines first. Then you can copy and paste after that. And you might have noticed the certain values that I said for y. I picked the start, high, the middle, the lowest, and then the end. If you can find those 5 points, you can make a pretty good sketch. So sometimes it's arbitrary how many points we find. We'll use the table on the calculator, and I'll tell you, find as many points as you need to make a good sketch. Well, here I'm pretty much telling you it's 5 every time. If you can find 5 points, specifically those 5 points, you can make a good sketch. So in this picture, just to be clear about what each axis represents, this is the x-axis, and this represents an angle. That's the y-axis, and in this case, the y-axis represents the sine of the x value, or the sine of the angle. So the x-axis is an angle, and the y-axis is the sine of that angle. It could also be the cosine, but this one is specifically sine. Now, if we don't do any kind of transformation to the graph, we don't stretch it, shift it, compress it, we don't transform it at all, the distance from here to here is a certain amount. And that distance is 2 pi. So the length of the interval that you have to travel before the graph will begin to repeat itself is 2 pi radians, or 360 degrees. So if you sketch a graph of sine from 0, let's say it in degrees, from 0 to 359. When you get to 360, think about it. The sine of 0 is going to be exactly the same as the sine of 360. The sine of 1 is going to be the same as the sine of 361. The sine of 2 is going to be the same as 362. So once you've gone beyond 359 degrees, all the answers that you get are going to start repeating themselves, because you can add 360 to any number and you get the same answer that you got before. Okay. Any question on that idea? Right? And then once you get to 719 degrees, you're at the very end of the second wave, and when you get to 720, you're now going to be repeating what you had at 360, which is a repetition of what you had at 0. All you've done is add 360 again. That's why the graph is exactly the same pattern repeated forever. We haven't studied any graphs that do this yet. This is the first one we've studied that repeats itself. So this is what we call the standard period length for sine and cosine. Now another name I've also been using a little bit is also called a cycle. Period is also called a cycle. There's no difference between the two words. You can use either one. So what you're looking at in green is one cycle of the sine function, or one full period. So let's say I wanted to look at my calculator and I only wanted to show one cycle of the sine function. I don't want to show several. Well, what did we just say that the standard length is for the cycle of sine and cosine? Yeah.
2 pi.
2 pi. So one way to show exactly one cycle, if you're in radians, is set your x min at 0, set your x max at 2 pi, and let's just change that, and hit graph. So I set an x min of 0 and an x max of 2 pi, one cycle. What if I wanted to see 2 cycles? What could I set my x max to? So I set 2 full cycles. Yeah.
4 pi.
4 pi. So now if I set it on 4 pi, I'm going to see 1/2, 3/4, 1 1/4, 1/2, 3/4, 2. That's 2 full cycles. Generally, if they want you to sketch something on the calculator, they'll tell you find a window that shows 2 cycles or 3 cycles. That's pretty common. All right, so we got that. All right, so graphing sine and cosine. I told you that in general you want to pick 5 points. These are the 5 points you want to pick. Because those points mark what I call the quarter points in the graph. The beginning, the end of the first quarter, the second quarter, the third quarter, and the fourth quarter. So by finding those 5 specific points, it really gives you everything that's important. It gives you all the x-intercepts, it gives you the high, and it gives you the low. And think about if you wanted to find the points here that separated, or the points that divided the sine function into its quarters, you would have to space the points out 90 degrees. 0 to 90 is the first quarter, 90 to 180 is the second quarter, 180 to 270 is the third quarter, and 270 to 360 is the fourth quarter. Now, I've used radians. Pi over 2 is 90, pi is 180, 3 pi over 2 is 270, and 2 pi is 360. So all these points are exactly pi over 2 radians, or 90 degrees, apart from each other. So anytime that we want to graph a transformation of sine or cosine, the way we're going to do it is you're only going to have to sketch one cycle. You're not going to have to sketch it, like that. You're not going to have to sketch like 7 cycles. All you're going to have to do is sketch one cycle. So we look kind of like that. That's what I'd be looking for. One cycle. Because if you can sketch one, you can copy and paste it and sketch more. Specifically, what you guys will be graphing is the first positive cycle for sine. Here is the first positive cycle, along with the first 5 points in that cycle. All I'm going to want to know when you do a transformation is what happens to these 5 points. That's it. Just those 5. So let's write down what these 5 points are. That's 0, 0. This is pi over 2, 1. This is pi comma, 0. 3 pi over 2, negative 1. And 2 pi, 0. Let's put those in a table, or let's organize them somehow. Okay, so whenever we graph a transformation of sine or cosine, start with the following table. The table I'm going to give you on the left is a table of these 5 points in that picture. Zero, 0. Pi over 2, 1. Pi, 0. 3 pi over 2, negative 1. And 2 pi, 0. Those are the 5 points in the first positive cycle for sine. So any transformation that we do will be done to those points. All right. Now let's think about cosine. Okay, cosine was a little different. It's still a wave, still between negative 1 and 1, but it starts at a different point. Cosine does not start at the origin. Let me bring up the calculator and let's look at cosine. Oh, so this is sine again. What you're going to see in red is cosine. Where does cosine start? Doesn't start at 0, 0. Starts at what? Yep.
1, 0. No, 0, 1.
0, 1. Yep. Starts at 0, 1. And this next one, this is pi over 2, pi, 3 pi over 2, 2 pi. How do I know that? I hit zoom 7 on the calculator. Zoom 7 is another window like zoom 6. But zoom 7 sets up what's called a trig window. It's just a special window so trig functions look good. Okay, so as Tyler just said, 0, 1. Pi over 2, 0. Pi, negative 1. 3 pi over 2, 0. 2 pi, 1. And we're back where we started. Those 5 points are the 5 points in that table. So if you have to do a transformation of sine, start with the table on the left. If you have to do a transformation of cosine, use the table on the right. And the nice thing about the transformations, when we get to them, every single transformation works exactly the same as all the transformations we've studied all year. There is no difference. But we are going to break down transformations even more than we normally do. Normally, when we do transformations, I just throw all the transformations at it in one day. We're going to really break it down. And today, we're not even going to do a problem that would have more than one transformation in it. Like a shift left and a shift up. Nope, that's 2. We're not even going to do 2 today. We're going to do one transformation per problem. And then we'll get into multi-step ones. That's exactly what I just told you. So when we do problems that only have individual transformations, let's go back to this table. Let's say I had you take the graph of sine and I said shift it up 2. Do a vertical shift up 2. Which column is affected by doing a vertical shift? The x column or the y column? Okay, the y's. And if that was the problem I gave you, shift up 2, that's all that would be in the problem. So the x column would be untouched in that problem. We wouldn't have to do anything to the x column in this table. All we'd have to do is shift all the y values up 2. So like 2, 3, 2, and so on. Just shift them up 2. But for each problem we do, one column will stay the same, and the other column will change. Until we do multi-step transformations. Then both columns will change. But for now, one column will stay the same, and the other column will change. So today we're going to focus on the 2 transformations that do shifting. Shifting left and right, shifting up and down. Tomorrow we'll focus on the 2 transformations that do the stretches, the vertical and the horizontal. So the first transformation that we're going to study, now that I've given you guys all the background information and the tables you need, the first transformation we're going to do is a phase shift. A phase shift is just another name for a horizontal shift. With trig functions, they call it a phase shift. We've always called it a horizontal shift. You can use either name, that's fine. But a phase shift is a translation. It's when the graph either moves left or right. And the first thing I'm always going to show you when we learn a transformation is how do you identify it? This is how you identify it. It's when you have an equation and you've done either addition or subtraction inside the argument, inside the parentheses. Adding or subtracting inside the parentheses is a horizontal shift. Now, based on what we've learned in the past, if I had x plus something, which way would the graph move? X plus. Yeah? It would move left. What if I had x minus? Okay? It would move to the right. It's the opposite, and it's still the opposite here. So if it's x minus, everything is going to shift to the right. How much? It depends on what you minus. There are common values that we usually plug in for a. We don't usually shift by just a random number. Since you're shifting left and right, the shift is by a certain amount of degrees or radians. Usually, the shifts that you're going to see are by 90, 45, or 180. In radians, pi over 2, pi over 4, and pi. Those are the common amounts that you'll see added or subtracted. Technically, could you shift it by 13.7 degrees? Yes. That's not a common amount we usually do. 90, 45, and 180. All right. And then if you have x plus, everything is going to shift to the left. So think about what's happening here. We're moving left and right. Think of the 2 columns in that table. If you move something left or right, what value in the coordinate is that going to change? The x value or the y value? If you slide something left or right. Yeah.
The x value?
It's going to change the x value. Yes. So our goal is going to be now, if I give you a problem like that, don't write it yet. How do we change the x values? It's a phase shift because we're subtracting inside the argument. I know the y values aren't going to change because I'm not moving it up and down. So how are the x values going to change? That's what we need to figure out. So how do you figure out the 5 new points? You've got the original points. That's in your table. Now we're going to find the new points. So, step one, when you're doing a phase shift, the y values in the original table do not change. So what I'm going to look for in your answer is, I'm going to look for a table. That's how the test will be set up. You're going to see a table. The y values would be copied down from the original table that I just gave you. Now, let's think about the x's. The x's are going to change. We've got to be careful when you do a phase shift, because it's the opposite of what you would think. So we're gonna do that one in a minute. Which way is the graph moving there? Is it moving to the left or is it moving to the right? Tyler?
To the right.
It's moving to the right. Now, think of a number line. What happens to values if they move right? Compare where they started to where they ended up. If they move to the right, they're getting bigger. They're getting bigger. If they're getting bigger, that means you need to add something to them. If you want to shift things to the right, which is what's supposed to happen here, you need to increase all your x values. If you were shifting to the left, all your x values would decrease. How do you decrease them? You subtract something. So basically, you have to do the opposite of what you see right there. If you see a minus, that means shift it to the right. If things are shifting to the right, they are increasing. So you have to add something. And that's how I just explained it right here. To find the new x values, look at what you're adding or subtracting. In this case, we are subtracting pi over 2. And then do the opposite of that. You want to move them all to the right, you need to add pi over 2. And that will shift them all to the right. So phase shift is one of the two transformations that it does the opposite of what you would expect. Vertical shift doesn't. Vertical shift is very straightforward. Just like it has been in the past. So let's try a few examples doing phase shift, and then we'll finish up with a vertical shift, which is easier. So, step one, identify what type of transformation this is. When you want to identify a transformation, you look for two things, what and where. Those are the two things you need to find. What's happening? Subtraction. Anytime you do adding or subtracting, it's always a shift. Where you're adding or subtracting tells you if it's horizontal or vertical. In this case, the where is inside the parentheses. So the what is a subtraction, and the where is inside. So it's a phase shift. We said everything is going to move to the right. So let me write down my original x values. I'm putting them off to the side. I'm going to leave a little room to do some work. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, what am I going to do to all these x values to take care of this phase shift? First of all, am I going to add or am I going to subtract? Okay? Yep, we're going to add. Adding will move things to the right, and that's exactly what you want to happen. How much do I add to all of those? How much am I going to move them? Yep,
Over 2.
pi over 2. No decimals in the final answer. No decimals. Okay, we want to leave everything as an exact answer. Okay, so first one, that's easy. 0 plus pi over 2 is pi over 2. Next one. Pi over 2 plus pi over 2. If you want to add fractions, what do you have to make sure you have? Yep,
Common denominator.
common denominator. We already have it here. You might need it later on, but this one's fine. And if you add pi over 2 to pi over 2, what do you get? Francesca?
2 pi over 2.
2 pi over 2. I am gonna reduce that, but I'll leave it off to the side with a denominator of 2, so you can see a pattern when we're done. Okay, next one. Pi plus pi over 2. Pi is not even a fraction, so what can you always put in the bottom to make something a fraction? Jake?
1.
You can put a 1. And what's my common denominator between 1 and 2? Yep,
2.
2. This already has a 2. What would you have to multiply top and bottom by to make that a 2? Yeah,
A 2.
a 2. So now I have 2 pi over 2 plus 1 pi over 2. Now, what's 2 pi over 2 plus 1 pi over 2?
3 pi over 2 and
So 3 pi over 2. Nothing to reduce in that case. Next one, we already have a common denominator. Let's not reduce it yet, because I want to see the pattern. Abigail, what's 3 pi over 2 plus 1 pi over 2?
Pi over 4.
So remember, when you add, your denominator doesn't change.
Over 2.
You keep that the same. So what's your numerator?
4 pi.
4 pi. And Jack, what does that reduce to?
2 pi over 1.
Yep, 2 pi over 1, or just 2 pi. Now, look at the pattern, and let's see if we can get the last one without even doing the common denominator. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Tyler?
5 pi over 2.
Yeah, 5 pi over 2. And if you were ever asked to graph another cycle, this is one full cycle, but if you had to do another one, just continue the pattern. 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2, 11 pi over 2. You can just keep going as long as you needed to. Now, remember the y values? The y's stayed the same. They didn't change. So all I need to know for the y's is if you flip back to the sine table, what were the original y values in that table? We could have written these down first. Jake?
0, 1, 0, -1, 0.
0, yeah. So there is your table. And the way that would be graded on the test, I give you 1 point for each x and y value you get right. So the table is worth 10 points. Any question on that? All right, now the sketch. So to sketch it, we need to label our axes, okay, what we're going to go by. The only condition when you label an axis is that you are consistent. You couldn't have a number line and do this. I mean, what are you going by? You going by 1s, 2s, 6s? I can't tell. So you have to go by the same thing every time. All of these x values, if you remember, were originally pi over 2 radians apart. If we took 5 things that were all equally spaced, and we shifted them all together. Are they still equally spaced? Is that Ethan?
Yeah.
Yeah, they're still equally spaced. And that's exactly the condition that you need if you want to use numbers to label your axis. I'm going to use those numbers to label my x-axis because they're equally spaced. So if I was doing it in degrees, this would be 0, 90, 180, 270, 360. It's a lot easier to use those as my labels than 0, 1, 2, 3, 4, 5. We don't want to do it like that. It's okay on the y-axis to go by ones. I think that's fine. And now we're just going to plot the points from that table on that graph. So pi over 2, 0. We've got pi 1. 3 pi over 2, back to 0. 2 pi, I'm at -1. And 3 pi, or 5 pi over 2, I didn't put that label, I should. 5 pi over 2, I'm back at 0. Just remember that this is a curve. There's nothing about these graphs that are linear. Shouldn't be any sharp points on them. Should be a nice smooth curve. And that is the new graph. And remember, that one was pushed to the right. The original would have been like this. Right, like that. So the original would have started at the origin, and we've shifted it 90 degrees to the right. I'm only interested in the table for the new graph, not the original. And this time I sketched both so you could see them, but a lot of times you're not going to have to sketch both. On the test, you definitely don't. There might be some on the homework. Yeah, you do. Okay. Any question on that one? All right, so let's try another phase shift. Okay, we did sine. Let's try cosine. Again, look for the what and the where. What are you doing? You're adding. Okay, it's a shift. Where are you doing it? Inside parentheses. Okay, it's horizontal. Horizontal shift. So, what column? Let's do the column that stays the same. What's going to stay the same this time? Tyler?
The X. Right?
Well, what kind of transformation are we doing?
The Y. Because it's shifting left.
Yeah, this is a horizontal shift, so this is still going to be the same thing we did last time. The x's are going to change. The y's stay the same. What are my original y values for sine? Ethan?
1, 0, -1, 0, 1.
Yep, 1, 0, -1, 0, 1. And what are my original x's for cosine? Let's put those way over on the side. Sarah?
Zero, pi over 2, pi over 2, and pi.
Okay. Now, let's decide, am I going to add or subtract to all of those? Francesca?
Are we going to subtract it?
We're going to subtract because we do want everything to shift left. And how much do I want everything to shift? Yeah, pi radians. Okay. Put all our answers in that box. Some of these we don't need common denominators for. The first one is -pi. The third one is 0. And the fifth one is just pi. Now, let's do common denominator. Bailey, what's the common denominator between 1 and 2? 2. 2? So we multiply top and bottom by 2. And Matt, what's 1 pi over 2 minus 2 pi over 2?
Negative.
Pi over 2.
Negative pi over 2. And we're going to do this one more time, except it's 3 pi over 2 instead of 1 pi over 2. That's the only difference. So what's 3 pi over 2 minus 2 pi over 2? Tyler?
Pi over 2.
Pi over 2. Were all of these x values equally spaced when we started? What do you think? Yeah, Jake?
Yeah.
Yes. 0, 90, 180, 270, 360. We shifted them all, but we shifted them all together. Are they still equally spaced? Yeah, they're just equally spaced in a different spot, but they're still equally spaced. So you can use those as your labels on your grid. So we need negative pi. I would put that one here. Negative pi over 2. And the axis is always 0. You can't change that. Don't ever label the axis anything other than 0. X or Y axis. We need pi over 2. And we need pi. Label your y-axis, 1 to negative 1. And if you have bigger graph paper, that's fine. I just drew this small grid because that's all you need. That's all you need. Okay, so negative pi, we're at 1. Negative pi over 2, 0. 0, negative 1. Pi over 2, back at 0. And pi, we're back at 1. Now, it does look like a V, but remember, it's not a V shape. It's a wave, and you're sketching the middle part of like a cycle. You're sketching kind of the dip in the wave. So try to make it look curved, kind of like, and that's good enough. Okay, but it should have some curvature to it. Right? And the original would have been shifted to the right because the new one moved to the left. Right, any questions on that one? So the last transformation we're going to do is a lot easier. When you're shifting left and right, first of all, you have to remember to do the odds. And you have to do arithmetic with the x column. Doing arithmetic with the x column is annoying because you have to deal with all these pi's. When we do a vertical shift, we don't have to do anything with the x column because it's moving up and down. We're going to be working with the y column. Think of the numbers in the y column. 1, 0, negative 1. It's very easy to do arithmetic with those three numbers. So, vertical shift will move the graph up or down. When we've studied functions in the past, what do we always look for to know that something is a vertical shift? Like, what do you look for and where do you look for it? Those are the two things. Yes?
Outside of the parentheses to the right.
Okay, so that's where we're going to look for it. What are we looking for? Yeah.
The positive or negative.
Adding or subtracting. So we're still looking for adding or subtracting. But this time, it's outside the argument. If you did that, it still means the same thing. I can just do that to clarify that it's outside the argument. And I use the letter D for an important reason. When we study multi-step transformations, you will probably be able to guess why I use D for that. Okay, so D is what we call the vertical shift amount. What you're adding or subtracting is outside the argument. I was going to ask you, but I guess I'm not. So when you add, that moves it up. And when you subtract, that moves it down. So there's no doing the opposite here. Don't do the opposite with a vertical shift. Do it just like you've been doing it all year. Plus is up, minus is down. Okay, so when we do a vertical shift, what values are going to be affected by that? When you shift something up and down, what values will change? Sarah?
More.
The y's. That's good. If the y's are changing, that means the x's are going to stay the same. So for every vertical shift problem we do today, in class and in the homework, here's the answer for the x column. 0, pi over 2, pi, 3 pi over 2, 2 pi. The x's will stay the same. Not for a phase shift, for a vertical shift. If the x's are staying the same, the y's are going to change. All you have to do is take whatever you had for your d value and add or subtract it to the original y's. If you had a plus 2, like this, you don't need to put parentheses around the x. That's still a vertical shift, just the way it is. This means to shift everything up 2. You would do a plus 2 to all your y values. If you had sine of x minus 2, you would do a minus 2. Don't do the opposite. Okay. Right, so we'll try a couple examples of a vertical shift, and that'll be it. Okay, so cosine x plus 2. Look for two things. What and where. What are you doing? Where are you doing it? What are we doing in this problem? What's the math operation we're doing? Okay?
Addition.
We're doing addition. Where are we doing it? Addition tells me it's a shift. But where is it happening? Yep.
Going up.
So where is it in the equation now?
On the outside.
It's on the outside, right? It's at the end. Since it's on the outside at the end, that tells me it's a vertical shift, and it is up 2. So, x's stay the same. Abigail, what are my original x values?
0, pi over 2,
And the last one again?
2 pi.
2 pi. Okay. Let's put the original cosine values down, but let's put them off to the side. Jack, what are my original y values for cosine?
Negative 5 or 0.
1. Yep.
0, negative 1, 0, 1.
Yep. So we got those. And Eli, what am I doing to all those y values?
Adding 2.
I'm going to add 2. Francesca, can you tell me what I get if I add 2 to all those values?
3, 2, 1, 2, 3.
There you go. So there are your new y values. That's why I said the arithmetic was a lot easier. 3, 2, 1, 2, 3. Any questions on the table? And let's do a sketch. So we need, our graph is going to be shifted up, so it's mostly going to be in quadrant 1. I try to put my labels in a spot where I'm not going to draw over them. putting them right here is fine. I don't need to go any higher than 3. 3, 2, 1, 2, 3. That's all I have to remember to sketch. 3, 2, 1, 2, 3. There you go. And there's your cosine function, shifted up 3 units. Any question on that one? Sorry. All right, so let's look at the last one. So sine of x minus 3. Okay. Zach, what's going to stay the same here?
The x.
Yep, x's are going to stay the same. Everything's going to come down 3. X's are not affected by shifting down. Eli, what? No, Eli. How about I just asked you a question? How about Bailey? What are my original x's?
Zero, pi over 2, pi, 3 pi over 2 pi.
2 pi. And Ethan, what are my original y values for sine?
0, 1, -1, 0, 1.
What's this one?
-1, 0.
And 0. Okay. And Tyler, what am I going to do to all those y values?
Subtract 3.
Yep. So -3. Let's see. -2, -3, -4, and -3. All right, let's make our sketch and we're done. This time, I'm going to put my labels up here. Zero, pi over 2 pi, 3 pi over 2, 2 pi. It's going to make it so I can see it all at once. That's easier. Then I'll make it bigger so you can see it. So this will be 0, -1, 2, 5. Oh, I don't need to go that way. I just need to go to -4. So -3, -2, -3, -4, -3. And there's your sketch. Questions on that? So those are the first 2 transformations for sine. So most of the homework is going to be a worksheet. Actually, you know what? It's going to be these questions. On Schoology, I think I had a different worksheet because I was at a different point when I thought I was planning it. Those are the questions for homework, and I'll make sure that's up on the video tonight. So ignore what's on Schoology. Try those 7 questions. And page 335, 45, 46, 55, 56. So you have 7, 8, 9, 10, you have 11 questions for homework.
Can I take a picture of it?
I'm going to put it up on YouTube. So if you want, just, yeah, I'll put it right up on there. I'll put it up right now.